Hey everyone, welcome back to our channel. Have you ever wondered why rainbows form? They're one of nature's most beautiful and mesmerizing phenomena, but there's some fascinating science behind those vibrant arcs of color. In today's video, we're going to dive into the world of rainbows, explore how they form, and uncover the secrets of their stunning colors. So stick around and let's get started. Rainbows are one of nature's most captivating spectacles. These vibrant arcs of color have fascinated humans for centuries, inspiring countless myths, legends, and scientific inquiries. They appear as arcs of color painted across the sky, often after a rainstorm, when the sun begins to shine through the lingering droplets of water. A reminder of the beauty and wonder that the natural world holds, rainbows are a fleeting yet profound sight that can transform an ordinary day into something magical. But have you ever stopped to wonder how these ethereal displays of light and water are formed? What processes in nature create such a stunning visual phenomenon? What is the science behind their dazzling colors and elusive nature? Understanding the formation of rainbows can deepen our appreciation for these natural wonders. Rainbows are formed by a fascinating interplay of sunlight and water droplets in the atmosphere. This interaction is a complex dance of light and water that results in the beautiful spectrum we see. When sunlight passes through these tiny prisms of water, it is refracted, reflected, and dispersed. Each droplet acts as a miniature prism, bending the light and splitting it into its component colors, creating the spectrum of colors we see in a rainbow. This process involves multiple reflections and refractions within each droplet, which combine to produce the vivid colors. This mesmerizing display is not merely a visual treat, but also a testament to the elegant laws of physics that govern our universe. The principles of optics and light behavior are beautifully illustrated in every rainbow. Join us as we delve into the science behind rainbows, exploring the optical phenomena that give rise to these celestial marvels. We'll look at how light behaves when it encounters water droplets and the conditions necessary for a rainbow to form, exploring the optical phenomena that give rise to these celestial marvels. We'll uncover the secrets of their colors, the specific angles and conditions that make rainbows visible, and why they appear as arcs. We'll uncover the secrets of their colors, the myths and legends associated with them, and the cultural significance they hold in various societies around the world. The myths and legends associated with them, from the pot of gold at the end of the rainbow to the bridge between worlds in Norse mythology. These stories add a layer of mystique to the scientific wonder, and how you can increase your chances of witnessing these fleeting wonders in the sky. We'll share tips on the best times and conditions for spotting rainbows, and how to capture their beauty on camera. So, the next time you're lucky enough to spot a rainbow, you'll be able to appreciate it with a deeper understanding of the magic that brings it to life. Whether it's a single arc or a rare double rainbow, each one is a unique display of nature's artistry. You'll be able to appreciate it with a deeper understanding of the magic that brings it to life. The interplay of light and water, the science and the stories, all come together to create a symphony of light and water that is truly awe-inspiring. The formation of a rainbow begins with a simple yet essential ingredient: sunlight. This sunlight, which we often take for granted, is the key to unlocking one of nature's most beautiful phenomena. Sunlight, although it appears white, is actually a blend of different colors. These colors are always present, but they are usually mixed together in such a way that we perceive the light as white. Each color of light travels at a slightly different wavelength. These wavelengths range from the shorter blue and violet to the longer red and orange. When sunlight passes through a prism, like a glass prism or even a water droplet, these different wavelengths are separated, revealing the full spectrum of colors. This separation is what allows us to see the individual colors that make up white light. Rainbows are nature's way of demonstrating this principle of light dispersion. They are a perfect example of how light can be broken down into its constituent parts. When sunlight shines through raindrops suspended in the air, it encounters these tiny spherical prisms. Each raindrop plays a crucial role in the creation of a rainbow. As the light enters a raindrop, it slows down and bends, a phenomenon known as refraction. This bending is the first step in the process of creating a rainbow. This bending causes the different wavelengths of light to separate. The shorter wavelengths bend more than the longer ones, causing the colors to spread out. The light then reflects off the back surface of the raindrop and travels back through the droplet, exiting into the air once more. This reflection is what gives the rainbow its characteristic arc shape. As it exits, it undergoes another refraction, further separating the colors. This second refraction enhances the separation of colors, making the rainbow more vivid. Each raindrop acts like a miniature prism, dispersing the sunlight into its constituent colors. The combined effect of millions of these tiny prisms creates the rainbow we see. This dispersed light is what we see as a rainbow. The colors spread out in a circular arc, with red on the outer edge and violet on the inner edge. The position of the sun, the angle at which the light strikes the raindrops, and the position of the observer all play crucial roles in determining whether or not a rainbow will be visible. For a rainbow to appear, the sun must be low in the sky, typically in the early morning or late afternoon. The observer must be positioned with their back to the sun, looking towards the rain. The angle at which the light enters and exits the raindrops must be just right to create the spectrum of colors. All these factors come together to create the magical sight of a rainbow, a fleeting yet unforgettable display of nature's beauty. To truly understand how rainbows form, we need to delve a little deeper into the science of light. Light is a fascinating phenomenon that has intrigued scientists and philosophers for centuries. It is both a wave and a particle, a duality that allows it to exhibit a range of behaviors under different conditions, and how it interacts with matter. Light, despite its intangible nature, behaves in predictable ways when it encounters different mediums like air, water, or glass. These interactions are governed by the principles of physics, which help us understand and predict the behavior of light in various scenarios. Two key phenomena at play in rainbow formation are refraction and reflection. These processes are fundamental to the way light behaves and are essential for the creation of the beautiful spectrum of colors we see in a rainbow. Refraction is the bending of light as it passes from one medium to another. This bending occurs because light changes speed when it moves between different substances. The amount of bending depends on the angle at which the light hits the new medium and the difference in density between the two mediums. This bending occurs because light travels at different speeds in different mediums. For example, light travels faster in air than in water. When light enters a denser medium, it slows down, causing it to change direction. This change in speed and direction is what we call refraction. When light passes from a less dense medium like air into a denser medium like water, it slows down and bends towards the normal, an imaginary line perpendicular to the surface where the two mediums meet. This bending towards the normal is a crucial part of how light behaves when it enters a new medium. Conversely, when light travels from a denser medium to a less dense medium, it speeds up and bends away from the normal. This speeding up and bending away is just as important in understanding how light interacts with different substances. Reflection, on the other hand, is the bouncing back of light when it encounters a surface. This can happen with any surface, but it is most noticeable with smooth, shiny surfaces like mirrors or calm water. When light strikes a smooth surface, it reflects at the same angle at which it struck the surface. This is a predictable behavior that allows us to understand and manipulate light in various ways. This is known as the law of reflection. According to this law, the angle of incidence, the angle at which the light hits the surface, is equal to the angle of reflection, the angle at which the light bounces off. In the context of a rainbow, both refraction and reflection are crucial. Without these two processes, the light would not be able to separate into the different colors that make up a rainbow. Refraction causes the separation of colors as light enters and exits the raindrop. This separation occurs because different colors of light bend by different amounts. Red light bends the least, while violet light bends the most, creating a spectrum of colors. While reflection off the back of the raindrop sends the light back towards the observer, allowing us to perceive the rainbow. This combination of refraction and reflection inside the raindrop is what creates the circular arc of colors that we see in the sky. The next time you see a rainbow, you'll know that it's not just a beautiful sight, but also a fascinating demonstration of the principles of light. Section 4. Unraveling the rainbow's palette. We often describe a rainbow as having 7 colors: red, orange, yellow, green, blue, indigo, and violet. This order is not arbitrary. but is determined by the wavelengths of these colors. Red light, with the longest wavelength, is bent the least, while violet light, with the shortest wavelength, is bent the most. This difference in bending is what creates the arc of colors we see in a rainbow. Red light appears at the top of the arc because it is refracted at a smaller angle. Violet light, on the other hand, is refracted at a larger angle and appears at the bottom of the arc. The other colors fall in between, creating the familiar rainbow spectrum. However, it's important to remember that the rainbow is a continuous spectrum of colors. Our eyes perceive distinct bands of color, but in reality there are countless shades and gradations between these bands. The perception of 7 distinct colors is more of a cultural construct influenced by the way we categorize and describe these colors. Section 5. Beyond the spectrum. A glimpse into the infrared and ultraviolet. While our eyes are only sensitive to the visible spectrum of light, rainbows actually contain a much broader range of electromagnetic radiation, including invisible wavelengths like infrared and ultraviolet light. Infrared radiation has wavelengths longer than red light and carries heat energy. Although we can't see infrared light, we can feel its warmth. Ultraviolet radiation, on the other hand, has wavelengths shorter than violet light and is responsible for sunburns. Even though we can't see these invisible components of the rainbow, they are still present and play a role in the overall phenomenon. Specialized instruments can be used to detect and measure these invisible wavelengths, revealing a hidden dimension to the rainbow's beauty. Thanks for joining us on this colorful journey to understand why rainbows form. We hope you enjoyed learning about the science behind these natural wonders as much as we did. If you liked this video, make sure to give it a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more amazing science content. Hit the bell icon so you never miss an update. Until next time, keep looking up and stay curious.